Hi, in this video, we are going to discuss about IIR filter structures, so infinite impulse response filter structures. Earlier we discussed FIR filter structures, which means they have only zeros, but IIR filter structures also have poles in them, which means there is a feedback loop in the structure. Okay, so what are IIR structures? So general equation for LCCDE equation or the representation is like this: a rational Z transform. You have some numerator and some denominator. You can write it as PZ into 1 upon DZ. So basically, uh, if I take the inverse Z transform and representing HZ as YZ upon XZ, then I get YN plus D1 YN minus 1 plus D2 YN minus 2 plus so on. This is equal to P naught xn plus P1 xn minus 1 plus P2, P2 xn minus 2, which is okay, all these terms. So what does this imply? I can rearrange it and write it as yn is equal to, so all the terms basically, P0, P1, and so on. And then the D1 terms also I take to the other side. It becomes minus D1 times yn minus 1 minus d2 and so on. Now the first part, this I can group and call it as u1, and the other part I can call it as v1. Okay, now now to write the structure, I can write it like this. So you see, on the left hand side I have an FIR filter. Basically it has only zeros. So if xn is my input, then this part has u1 as my output. Remember, u1 was just the numerator part, or just the terms with p0, p1, p2. So I have implemented just that part. And the next part is, uh, here my, it's basically v1 is the feedback, and I get u1 plus v1 here. So this means my yn. So my yn is actually u1 plus v1, right? And the u1 is coming from the FIR filter, and the v1 part is coming from the all pole IIR filter. Okay, so this is my direct form 1, which is basically PZ into 1 upon DZ. Now I can uh, exchange the PZ and DZ, and I can make it as 1 upon DZ into PZ. Basically I implement 1 upon DZ part first and PZ part later. So what happens is, the, you see, minus D1 minus D2 terms have come before, and the P1, P0, P2 term have come later. So what benefit it gives? So the best benefit is that we have merged our Z inverse filters, and I need less delay filters, which means less memory is required now, and there are same signals. So which means this is a very efficient way to minimize my number of memory requirement, or number of delay blocks required. Okay, so pictorially you can see the left part, FIR part, has come later, and the minus D1, D2 has come before. Okay, so now my IIR filter structure. So this is my, we have seen DF1 and DF2. Now if we take the transpose of DF2, what does it become? So on the left hand side you are seeing the DF2 structure, and on the right hand side I've just taken the transpose. So what is transpose? I replace my summation with a dot, and my, all the signs are, all the directions are reversed. My filters are reversed, and my XY are reversed. All the arrows are also reversed, right? So my dots become summation become dots, and then all the filters input output are reversed, and XY are also reversed. All the arrows are reversed. Okay, now this is my DF2 transpose implementation. Now, so far we have seen hz as numerator upon denominator, and we have implemented that part. Now we can also factor out, right? I can factor out my denominator in terms, the factors, like individual poles and zeros. Okay, that is good. But what happens if I have imaginary poles or imaginary zeros? Then this means that each factor will become will have imaginary parts. Okay, so let me first explain what do I mean. So I can break my hz into h1z into h2z and so on so forth, right? So this is very nice because then I am able to break it more. We will see the benefits that we can reuse different terms. Uh, and also it helps us to do stability analysis and things like that, like which block or which pole or zero is causing some problems, if any, and we can debug the system. So many advantages are there. Okay, now uh, if I do it this way and I separate each pole and zero, then it is possible some poles and zeros are imaginary, and I do not want my hz to have imaginary components, because then it will be difficult to implement it, right? How do I implement imaginary terms with my filters and all, right? So what I do is I I know that since my hz has uh, real coefficients, so this means my poles and zeros, they will always occur in conjugate symmetric pairs, right? And I can merge a conjugate symmetric pair to get real coefficients. That is why we can always group into second order terms with real coefficients. So which means my each term will be either uh, degree 0, degree 1, or degree 2. Means either zeroth order, first order, or second order terms. And I won't have third order. I don't need to have third order terms. So means by implementing second order terms, I can ensure that my hz or each hiz will have real coefficients. So my each hiz should have real coefficients. Okay. Now, um, so this is how the implementation will look like then, because now I'm breaking my h into h1, h2, h3. So you can see my h1 is simply p naught, h2 is made up of alpha 1 and minus gamma 1, h3 is made up of alpha 2, gamma 2, and beta 2, and delta 2. And in this way I can keep adding sections. So this has got second order section, which is highlighted in blue. So what is second order section? It has got uh, it is modular, and it has it is well behaved because there are no imaginary coefficients and all are real coefficients. And let's discuss more about second order sections now. So what are second order sections? So basically you have got a free choice. I will give an example here. Imagine my HZ is, it has two poles and two zeros. The poles are at A1, A2, and zeros are at B1, P2. Now if I have to break it into H1, H2, basically into two blocks, H1Z and H2Z, then how can I do it? I can either group uh, B1 with A1 and call this fraction as H1 and the other fraction as H2, or else I can group B2 and A1 and I can call this as my fraction h1 and the other as h2, right? So I have got a free choice. I can group poles and zeros in different ways, and also I can find the order of sections. Do I want to put h1 before or h2 before, right? So this is my free choice available to me now. uh, what I can do with this free choice, I have to optimize the numerical properties. For example, if I choose some poles or some zero combination in such a way that my one output of one block is very large and the output of the next block is very small. Of course the product is somewhere in between, but each block has either very large value or very small value, so I can have either overflow or underflow, which means quantization errors. So therefore my, because it's a digital computer, the whole thing will propagate and things will not be nice. So that is why I can choose them a little systematically. So there is a MATLAB has a function called ZP2SOS, but we are using Python. We have ZPK2SOS. So it attempts to put the roots and poles together. I will show you. Okay, so this is what I mean that let's say this is my on the left hand side is my original system. It has got two pole zero pairs. Means there are two pole pairs and two zero pairs, and I can factorize it either way. Factorization one is one option where poles and zeros are far apart. What do I see in one case? When the poles are very close to my unit circle, I get very large values, right? So these are the very large values. And on the other hand, when the poles are slightly away from the unit circle, I get little smaller values. But what I can do is in factorization 2 now, you see, I choose my pole zero pair for my H1, let us say, in such a way that my poles and zeros are very close so that the overall gain or overall the overshoot becomes small. Okay, so my in the magnitude response at zero point 0.2 omega, which means zero point 0.2 pi omega, it is controllable, means it's not very large. And similarly, the second part, again at around zero point 0.4 pi, there the magnitude response is not very large. So this means that I can choose my poles and zero pairs. I can group them together properly so that each block H1 as well as H2, they have got the values don't overflow or underflow, right? So let's see how we do it in Python. In Python, there is a function called ZPK2SOS, which is a part of signal library. So let us say on the what we see the pole zero plot, I have got 6 poles and 6 zeros, right? So this is the scheme which ZPK2SOS uses. Start from the pole nearest to the unit circle, which means the poles, the topmost and the bottommost poles, and pair with the closest zero, and that will help you to minimize the peak or the overflow. So this means I get a figure like this. Okay, I took a proper pair and then go to the next farthest pole and I get another pair, and then go to the next farthest pole and I get another pair. So this is my H1, H2 and H3. So I have broken down my H into three subsystems which I can uh, cascade together or put them in series so that I will get a nice HZ filter. So if you want to read further about this, you can read the documentation of ZPK2SOS, but I think this is sufficient. Okay. Now, parallel IIR structures. So what are parallel IIR structures? Basically, instead of breaking them into products, I can break them. I can instead of breaking my HZ into products, I can break my HZ into sum of terms. So uh, you have read about factorization when we were studying inverse Z transforms, right? So here what we are doing is we factorize each either first order term, second order term, or the no order, I mean, zero order terms. But this is the idea that this suggests the parallel realization. So this suggests the, so I will show you what is the benefit. So this is how the parallel realization looks like. So the topmost part is my H1, the middle section is my H2, and the bottommost section is my H3, let us say, right? So the sum terms, they become parallel paths. And so, what are the poles here? The poles are the same as the original HZ poles, right? Poles, the H1 poles and H2 poles. So these poles are same as what we had in HC. But the zeros, the system zeros arise from output sum. So these zeros are not the same as the zeros of HC, because when we factorize, our zeros will change. Uh, so let us say if I have my first order terms, they will have no zeros. If I have my second order terms, they will have 1 0, right? And these zeros, we don't have to choose or design them. They are just arise from the factorization process. Okay. Now, why do we do this? What is the benefit of parallel structures? So one benefit is that, okay, so no free choice. Now, one benefit of this parallel structure is that uh, system is stable. and it is a nice balance between stability and sensitivity, because sum is generally more stable than product, right? And this parallel IIR structures, they have sum terms, summation terms, so that it is more stable and easy to debug, right? If some part is overflowing, you can redesign it and easily debug it. And then next is we can reuse common terms. So what does that mean? I will go to the next slide to explain that. So what it means is, let us say I have got x1z, and I feed it into a filter h1 and h2 and h3, and I have got another x2z, and I can feed it into h4 and h5. And let us say my yz is this. It has got h4x2 plus h3x1 plus h2x1 plus h1x1, and that is my y1, right? And I have got some other y2, which is basically h5x2 plus h3x1. So you can see here my uh, x1 h3 is being reused. I can reuse it, right? So this is the idea, that the benefit which IIR structure offers, a parallel IIR structure offers. Okay. Now these are the references which you can refer to. It's chapter 6 of Oppenheim book, or Dan Ellis L07 chapter. Thank you very much.